Hey everyone, in this lesson you'll learn about a new family of functions, exponential functions. You may have been introduced to this type of function before, but we're going to look at the characteristics of the graphs of exponential functions and classify them as either growth or decay. We're also going to look at some applications of exponential functions in the financial world. So let's define an exponential function. So an exponential function is just a function in the form y equals a times b to the x power, and a will not equal 0, and b, the base, is any positive real number other than 1. The parent function here would be just f of x equals b to the x. All right, so I want you to get out your graphing calculators, and we are going to graph 4 exponential functions, and I want you to just tell me what you notice about each of these curves. How are they different? How are they alike? And what can you conclude about exponential growth versus decay? If you're not sure how to type this in, find the little caret, this little arrow. That's going to allow you to type in an exponent. So you can do 2 to the power of x this way. So you might have graphed these one at a time or all together, but here are the 4 graphs all together. So you should have noticed some similarities between the graph of function 1 and 3, 2 to the x and 4.5 to the x. So each of these should have had the same general shape when you graphed these functions. And if you could guess whether this represents growth or decay, I hope you would say these represent exponential growth. So in general, we can say whenever the b value there is greater than 1, that's going to give us an exponential growth model. So this curve represents exponential growth because it grows literally from left to right. So it rises from left to right. Another characteristic about this curve is that it has an asymptote at the x-axis and that it passes through the points 0, 1 and 1, b. Okay, you also should have noticed similarities between graphs 2 and 4, y equals 1/2 to the x and y equals 0.25 to the x. Each of these curves demonstrated exponential decay. If you'll notice, each of these b values are between 0 and 1. So anytime b is between 0 and 1, you're going to have exponential decay. So this characteristic is that the graph will fall from left to right, but it also shares some things in common with the exponential growth model. These curves also pass through 0, 1, and 1b, and have an asymptote at the x-axis. You should also be comfortable with graphing these types of functions without your calculator, and we can do this simply by making an XY table. So I would just choose a few basic points. Let's start with just 0 and 1. If you evaluate y equals 2 to the x at 0 and 1, you get the coordinates 0, 1, and 1, 2. So all we have to do is plot those points and just keep in mind the general shape of this exponential growth curve, knowing that there's an asymptote at the x-axis, and you have your graph. We can do the exact same thing in this second example for y equals 1/2 to the x. We're just going to make an xy table, plot some points. So again, I'll just choose 0 and 1. So if I evaluate 1/2 to the 0 power, I get 1 again, and 1/2 to the 1 power, I get 1/2. So we're just going to plot those points, and then knowing that this is an exponential decay curve, I know generally what it should look like. So after I plot my 2 points, I can connect that smooth curve so that it has an asymptote at the x-axis and it falls from left to right. Okay, so in general, we have these real-world situations where we need to use exponential growth and decay models. And so those general models that we see are y equals a times 1 plus r to the t and y equals a times 1 minus r to the t. So a, in this case, represents the initial amount of something. R represents the percent increase or decrease, whether it's growth or decay. And y is the total amount of the quantity after t number of years. There are many real-life quantities that increase or decrease by a fixed percent over a period of time, but one that's really relatable is savings accounts and putting money in the bank. And some savings accounts will pay you interest for leaving your money in the bank. So we're going to look at the compound interest formula, which tells you how much money will you have in the bank after a certain period of time, depending on the interest rate. P represents the principal or initial amount of money. The R represents the annual rate of interest, and this percent is written as a decimal in the formula. N represents the number of times that the interest is compounded per year. And that just means how many times the interest is paid out or calculated in 1 year. And then T just represents the total number of years that the money is left in the account. All right, let's do a couple examples using these exponential models. So in this example, we're looking at the value of a car in thousands of dollars. And that model is y equals 25 times 0.85 to the t power. T represents the number of years since the car was new. So you could imagine this car is depreciating over time, so it's losing value. But just looking at the model, you'll notice when it asks in part A whether this is growth or decay, this is clearly a decay model because of the b value in the exponential function. The b value is between 0 and 1. So that's how we know that this is a decay model. Now we need to identify the percent increase or decrease in the value of the car. So in order to do this, we want to look at the general decay model, a times 1 minus r to the t, and try to kind of fit our model into this general model. So we'll have to rewrite that 0.85 as 1 minus a number. So just calculate that number by doing 1 minus 0.85 and you'll get 0.15. So we can see that this percent decrease is 15%. Now to estimate when the value of the car will be $8,000, we're going to look at this model in our graphing calculators. So go ahead and type that into your calculator and let's look at the graph of this exponential model. We can use the trace feature in your calculator. You'll see the trace button next to graph, and that lets you just highlight any point on the curve. So when you see where your cursor hits the y coordinate of 8,000, that matching x coordinate is going to tell you when the car's value is 8,000. So you'll see the x coordinate here is 7, which means the answer to this question is the car's value will be $8,000 after 7 years. Example 4. Let's rewrite the exponential function y equals a times 0.5 to the t over 28 into our general exponential model of a times 1 plus r to the t or a times 1 minus r to the t. So we're going to go ahead and use properties of exponents first, and let's just rewrite t over 28 as 1 over 28 times t. That's going to allow me then to rewrite that piece in the middle, 0.5 to the 1/28th power, as a single number. So we're going to calculate that in our calculators. Just do 0.5 to the 1 over 28 power by using the caret, and you'll get 0.9755. So now to put it in that format of 1 minus, we know we're using the decay model because that b value is between 0 and 1. So we're going to rewrite this as 1 minus a number. So then to put it in the general model format, we have a times 1 minus 0.0245 to the t power. What this means is we can look at this version of that model and know right away what the percent decrease is of this model. So we can see that it has a decrease of 2.45%. All right, let's just do one more example and we'll use our compound interest formula. So suppose you deposit $9,000 in an account and it pays 1.46% annual interest. We want to find the balance after 3 years. That's a pretty good interest rate, actually. So if we go ahead and use our compound interest formula, A equals P times 1 plus R over N to the NT power, we just have to figure out what all of these numerical values represent in the formula. So P in this case is that initial amount of 9,000. R is the 1.46% as a decimal, so 0.0146. The 3 years is my T, or my amount of time. And then when it says quarterly, that just means 4 times in a year, so N equals 4. So go ahead and just take each of those values and substitute them into the compound interest formula and type that into your calculator. If you type it in correctly, you'll be able to figure out how much money will be in the account after 3 years. So you should get a grand total of $9,402.21. So just for leaving your money in that account for 3 years, you just gained $400. All right, that's it for this lesson on exponential growth and decay. Thanks for watching.